today we are just going to cover the basic probability rules. We'll probably do this for about 2 days. This is going to carry over into Thursday a little bit, um, but this is kind of part one of our basic probability rules. So, one thing we have to know about probability is chance behavior is unpredictable in the short run. However, in the long run, it will eventually have a predictable pattern. And what we do is we call this the law of large numbers. If I were to be flipping a coin, I may, in the short run, get 90% heads. But in the long run, if I were to do it millions of times, I am going to get closer to that predicted 50% chance of heads, 50% chance of tails. So remember, we cannot predict data or predict probabilities in the short run. We're always thinking long term. So there are two types of probability to describe. We have empirical and we have theoretical. So empirical is going to be based on actual observations, meaning data that you actually collect. So for example, you flip a coin 500 times, you get it 489, and your empirical probability is 489 out of 500. Then you move on to theoretical probability. So empirical is going to be based on an actual observation, but theoretical is based on an infinite number of trials, kind of just what I was describing. So if we were to keep flipping that coin over and over and over again, half of them should eventually, over time, be heads. So the theoretical probability would be 0.5. They don't always match. Sometimes they happen to do, more often they do not. So you do have two possible types of probabilities. Now, some things that go into basic probability rules. A lot of the times they do like to throw this onto the AP exam as those, which of the following are true? One and two, one, two, and three, those types of questions. So the probability of any event is between 0, meaning it will never happen, and 1, meaning it will always happen. So we think of these in terms of decimals, but if I were to turn it into a percent, 0%, 100%. So what we can say is that our probability of an event is always going to fall between 0 and 1. Anytime you are given a probability that is outside of this range, it's not valid. I can't have a negative probability, even though you think something really isn't going to happen. It's just a small chance, not negative. Even if you think something is absolutely guaranteed to happen, never going to exceed 100. So has to be between 0 and 1. The probability of an event in the long run proportion of repetitions on which the event occurs, the running theme of today, and all possible outcomes together must have probabilities that add up to 1. Something we call this is, which I'll talk about in just a second, the probability of the entire sample space is going to be equal to 1. So when I take all of the events and all of their probabilities and I add them together, it has to equal 1. I have to take care of every possible outcome in probability calculation. If you have anything less than 1 or anything greater than 1, it's not a valid probability model. Now, the probability that an event, and typically when we are describing events and probabilities, we have them labeled as a capital letter. So you'll see me often use A, and B. You could have something that's more related to what you're talking about, but we usually denote this by capital letters. The probability that an event A does not occur is 1 minus the probability of it occurring. So this is that it does occur, which makes sense because if my entire probability model is going to total to 1 and I know the probability of it occurring, I could take that, subtract it, and tell you the probability that it doesn't. And we often denote this as A with a little superscript of C, meaning it is the complement of the event. Another thing that you should be familiar with that will most likely pop up in a probability question is the formula: the probability of A complement is equal to 1 minus the probability of A. Basically, that's taking these two principles, putting them together into a handy-dandy formula. And a lot of this is going to seem intuitive because you've probably seen it in a simpler form at one point in time in a previous math class, but it is always good to go over it one more time. Now, we've talked about some basic things. Probabilities have to be between 0 and 1. They have to total up to 1. If I want to know the complement, I just subtract it from 1. Another thing that often gets asked is, are these events mutually exclusive? Another term for mutually exclusive, and it really depends on the year of the AP exam. They do go back and forth between these terms. They can't decide which one they favor the most. They both mean the same thing. If two events have no outcomes in common, meaning they do not occur at the same time. My best example for disjoint events is that you cannot be a sophomore in high school and a senior in high school at the same time. Those are disjoint events. You can't be a cat and a dog at the same time unless you're Cat Dog, the cartoon from Miss Contreras' childhood. Oh my gosh, I'm getting old. The probability that one or the other occurs is the sum of their individual properties. And we're going to put that into a formula in just a second. But just make sure you know disjoint means they cannot happen at the same time. When two events have no outcomes in common, we refer to them as mutually exclusive or disjoint. In other words, the probability of A and B happening is equivalent to 0, meaning they cannot occur together. Another big key idea to take from this: disjoint, mutually exclusive, cannot happen at the same time. Now, a simple probability formula that we are going to use only in the instance when we have equally likely events, meaning every single event has the same probability of occurring, is going to be the probability of event E is the number of outcomes in the event divided by the sample space. And this is just the basic probability formula. A lot of the times when you do actually get into these probability problems, you are not going to have this property of them being equally likely. Like when I roll a dice, it's equally likely for me to get each face of the dice, or flipping a coin. A lot of those things that we did when we were doing randomness with our simulations, that falls into this category. And again, one quick reminder, your sample space is the set of all possible outcomes. We usually call this S, like I did up top where I said the probability of the entire sample space has to be equal to 1. Now, one thing I do want to cover, which we did kind of briefly talk about when we touched on probability in the fall, was that there are some myths kind of surrounding probability. They do like to ask about this on the AP exam. They do like to see if you know that these things are not true. So the first one we've kind of touched on, the myth of short run regularity, the idea of probability that it's predictable in the long run, at least 1 million repetitions. Probability does not allow us to make short run predictions. Very, very important. We cannot make any predictions based on repetitions that are only like 5 or 10 or even 100. It has to be thousands and thousands and thousands of repetitions for us to get the true probability of an event. Another thing that often comes up is the myth of the law of averages. So, probability tells us that random behavior evens out in the long run. Future outcomes are not affected by past behavior. That's the big thing to take away from this. A lot of times, the example of gender is used because Your mom has had boys 4 times in a row. She's due for a girl. Does not matter what happened before. Does not matter if she had 20 boys. The probability of getting a boy or a girl is still 50-50. So you are not due for anything. Weather is also an example that's used often. Man, it's been hot 10 days in a row. We have to have at least one day where it's cool. Not necessarily. Not in Texas. Maybe in Texas these days, but most of the time not. So, two things to be careful of. They do like to ask this in multiple choice of, is so and so due for winning a baseball game? No. Law of averages is false. It is not true. Okay, let's go ahead and move on to talk about one of our first probability rules. I am going to cover a basic probability problem before we get there. A coin is flipped 3 times and the result of each flip is noted. And I know this is something that we kind of struggled with when we were doing simulation. So I will take a day where we break down tree diagrams and how to organize your information. But for now, I'm going to provide you with the sample space. So if I were to flip a coin 3 times, there are 8 possible outcomes that I could get from flipping that coin. And sample spaces are going to be denoted typically with S and with your curly brackets, commas in between your possible outcomes. So, what is the probability that exactly one of the flips results in a head? So, I am doing the probability of one head. And if you don't want to go through and say event A is getting one head, you can just fill in the words into the probability statement. That also works. So what I'm going to do is I'm going to look at my options and I'm going to see which one of these have only one head in the 3 flips. And so that comes from heads, tails, 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 heads, tails, 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 heads. So I have an entire sample space of 8. 3 of the outcomes meet what I want. So my probability is 3/8. And then we are going to do what is the probability that at least one of the flips results in a head. And this tends to be one where students kind of get confused with the wording. It just means that one or more of the flips would be a head. Now, you can think of this in terms of, does it meet this criteria? So I could go in and I could say, well, there's one head, one head, one head, one head, one head, one head, one head. And I know my probability is going to be 7/8, but you can also think of it in reverse. You can think of, okay, if I know I want one or more head, all I have to do is look at the times where that doesn't happen. And that's the complement, meaning I can subtract it from 1. We'll get into it a little bit more once we get all of the rules under our tool belt. But there's only one outcome that isn't in this event, and that is TTT, where you flip 3 tails. Okay, so basic probability. Now we're going to start looking at one of our first rules. Imagine rolling 2 fair, 6-sided die, 1 red and 1 white. What is the probability of rolling a sum of 5 or 2 even numbers? So sometimes it is beneficial to just label your events so that you're not writing out what your probability statement is every single time. So I am going to say A is going to be rolling a sum of 5 and B is rolling 2 even numbers. And I know that if I want to add to 5, I can't be adding 2 even numbers. That doesn't work mathematically. So both events cannot occur together, meaning that events A and B are mutually exclusive. They're disjoint. They're not happening at the same time. And if it's something that's not intuitive, meaning it's not something you could figure out yourself, a lot of the times the question will tell you these two things cannot happen together. So if I want to find the probability of rolling a sum of five or two even numbers, all I have to do is take the probability of A and add it to the probability of B. So probability of A or B. Oops, I'm going to lose everything. We'll come down here. There we go. Probability of A or B, I'm just going to take the probability of A, add it to the probability of B, and I have already gone ahead and picked out, it's going to look a little hard to see just because the red doesn't show up as nicely. Probability of A, rolling a sum of five, occurs 1, 2, 3, 4 times. And the probability of getting two even numbers occurs 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And in total, my sample space is 36 outcomes. So probability of A plus B is 4 over 36 plus 9 over 36, which gives me 13 over 36. So the probability of rolling a sum of five or two even numbers is 13 over 36. And what comes from this is our first part of the addition rule. So if I have mutually exclusive events, meaning they do not occur together, my formula is going to be the probability of A or B is equal to the probability of A plus the probability of B. And I'm going to give you a little bit of time to copy this down. And if this were something where they do ask you a question like this, they would provide you with an image similar to this dice image. A lot of the times they try not to work under the assumption that you know about outside factors. So hopefully, I would imagine and assume that they would provide you with something similar to this. So you didn't have to go in and draw out 36 possible outcomes for dice. Okay, let's go ahead and look at another question. So, online courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who is taking an online course and record the student's age. Here is the probability model. So, I have my possible outcomes, my possible events, and I have their probability of occurrence. The first thing is to show that this is a legitimate probability model, and a legitimate probability model will add up to 1. So all of the probabilities together should combine to a total of 1. So I'm going to take every single probability, add it up, and when I do, it turns out to be 1. So yes, this is a legitimate probability model. They do like to ask this question. It's one of their throwaways in FRQs. This is one you don't want to miss. Just add it up to 1, see if it works, see if it doesn't. Typically, if it's in an FRQ, I would say it's going to work because you're going to go on and do other parts, but maybe they'll switch it up. So now we are going to find the probability that the chosen student is not, meaning the complement of in the traditional college age group, which is 18 to 23 years. So I want the probability that they are not college aged, which I can find by doing 1 minus the probability of being college aged, which is 1 minus 0.57, which is 0.43. Now, the benefit of doing complements is when you have a ton of possible events, a ton of different events that could happen in your sample space, you don't want to have to go the route of, yes, I could go through and I could add up all of the other probabilities and I'm going to get the same answer. But you may not want to do that when you have 10 possible outcomes. It may just be easier to do 1 minus the probability of it occurring or it not occurring, depending on what you're asked. Either way works. Either way would suffice on the AP exam and on a test. Just depends on your manner of thinking. Gonna give you a couple of seconds. And what I will do is I always post my PDF at the end of the day just in case you happen to miss something that I write along the way. I know here in first period we move a little bit quicker just because I don't want to take up your whole hour. Okay, imagine rolling two fair six-sided dice, one red and one white. What is the probability of rolling a sum of six or two even numbers? So I'm going to go through a similar process that I did with number two. I'm going to label both of my events just so that I don't have to keep rewriting things. A is going to be rolling a sum of six. B is going to be rolling two even numbers. Now, this value has changed. It's no longer 5. So I can get a sum of 6 by rolling two even numbers. So now they have outcomes in common, meaning I'm going to have an overlap. So let's go ahead and just get the probabilities of each event individually. So I have the probability of event A is 5 over 36, which is 1, 2, 3, 4, 5 of my combinations. And I already know the probability of event B because it's the exact same one I used in example 2, and that is 9 over 36. And if I want to get the probability of one or the other, I could follow a similar path. I could do the probability of A or B is 5 over 36 plus 9 over 36, which is equal to 14 over 36. The only thing that happens is we run into the issue of these two. One second. We run into the issue of these guys here and here. Both of these events were counted twice. Both of these outcomes are counted for rolling a sum of 6 and rolling two even numbers. So what we want to do is we want to take away that overlap. So I'm going to subtract by those two times it was counted over and get my true probability of 12 over 36. And another thing that you could do in this instance is you could just go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 out of 36 because our sample size was 36 outcomes, 1 over 3. So anytime you have events that are not mutually exclusive, you are going to have some type of overlap that you have to account for. So our general addition rule is going to be the probability of A or B is the probability of A plus the probability of B minus that overlap. just so that we do not count it twice. And one thing you can do is if you don't want to have to worry about, am I dealing with mutually exclusive formulas or am I dealing with just the general formula? You can just focus on remembering the general addition rule, because if you remember, if A and B are mutually exclusive, the probability of both of those things occurring is zero. So I would just do A plus B minus zero, which is how we get our addition rule for mutually exclusive events formula. So you can just focus on knowing this one, and every time you encounter mutually exclusive events, this portion will be zeroed out. And oftentimes on the AP exam, if they do provide you with an image, it is evidence enough that you note on the actual image itself how you are calculating probabilities. A lot of the time, I always suggest still following up with your proportions, with your fractions, just because it does give them a little bit more opportunity to award you with partial credit. I know it's not called partial credit on the AP exam, but it does kind of push you, if you're in between a 3 and a 4, pushes you up to a 4 for that FRQ. And especially on my test, I do award partial credit. So if I see that you've set up and you got to 14 over 36, but you forgot the overlap, you're still going to get a majority of the credit. Okay, one thing I did want to include for my people who are not familiar with playing cards, this is just a image of a standard deck of cards. I typically give you a copy of this or I have a class set of like laminated ones in class for you guys to use. Not going to happen this year, so just wanted to put this in here so you could reference what a standard deck of cards looks like, because not all of us know what makes up a standard deck of cards, and that's okay. Again, AP exam would probably provide you with something like this if they were to ask a question about playing cards. So, example 5, a card is selected at random from a deck of 52 cards. Determine if the following events are mutually exclusive and then find the probability of the events. So, my first one is, what is the probability of red or queen? Well, first thing I'm going to do is determine, is it mutually exclusive or is it not? Well, I do have queens that are red. So that means they happen at the same time. This is not mutually exclusive. So when I'm doing not mutually exclusive, I have to remember that there's an overlap that I have to subtract. So I'm going to do the probability of red plus the probability of queen minus the probability of red and queen. Going to get my actual probabilities. So the probability of red, there's 13 of each suit. So 26 out of 52. The probability of queens, there's only 4 queens out of 52, so plus 4 over 52. And remember, these 2 red queens were counted in each of these probabilities, so I need to subtract one set, minus 2 over 52, which is going to give me 28 over 52, which is approximately 53.85. You could say 0.5385. Typically, the difference comes from how they phrase the question, which this one doesn't phrase it in any way, so it would be accepted either. If they say proportion, they generally want either the fraction or the decimal. If they say percent, of course, they want a percent. What is the proportion of cards that are red or queen? I'd probably give them 0.5385. What is the percent of cards? 53.85. For the most part on my test, I don't necessarily dock you for that, but it could be something that comes up on the AP exam that they get nitpicky about. So, what is the probability of ace or king? Well, you can't be an ace and a king at the same time, so these are mutually exclusive events. I do not have to worry about the overlap, so I can just go straight into probability of ace plus the probability of king, which is there are 4 aces and 4 kings, so 4 over 52 plus 4 over 52, which is going to result in 8 over 52, or approximately 15.38%. For part C, what is the probability of a queen or an even? Well, queen and evens are not going to happen at the same time because you're either a queen or you're a number. And so they're mutually exclusive. So I just need to get the probabilities of each. So I have probability of queens, which is going to be 4 out of 52. If I were to go up and look at my image, I could count out 20 even cards. And typically for questions like this, we do not consider the ace to be a value, even though it's 1. Just wanted to make a note there. We consider it as ace. I know sometimes card rules change. So 4 out of 52 plus 20 out of 52 is equal to 24 out of 52, which is approximately 46.15%. Okay, black or odd. Well, I can have an odd numbered card that is black. So, because of that, these are not mutually exclusive events. I have to deal with the overlap. So, I'm doing the probability of black plus the probability of odd minus the probability of black and odd. So, going to go and figure out my probabilities. There's 26 black cards. There are 16 odd cards. And that's the reason why I mentioned the 1, because we do not consider the ace to be a 1. So there's only 16, minus the probability of black and odd, which was 8, equals to 34 over 52, which is approximately 65.38. And I will say, if there were a question on the AP exam dealing with playing cards, you are going to have them, they will define that ace is either considered as a number value or just as an ace card. Typically, they do include some sort of statement because they do know that some people consider it to be 1. Okay, so I'm going to go ahead and go on to example 6. We have a two-way table. Students in an urban school were curious about how many children regularly eat breakfast. They conducted a survey asking, "Do you eat breakfast on a regular basis?" All 595 students in the school responded. The resulting data are shown in the two-way table below. So we are just going to take our probability that we've discussed, our rules, and apply it if our information were presented in a two-way table rather than as probabilities. So I have a total 595, that's going to be my sample space. What is the probability of getting a female? So all I have to do is go to the total for females. I get 275 out of 595, which is approximately 46.22%. What is the probability of someone who eats breakfast regularly? So all I'm going to do is go to my eats breakfast regularly row, look at my total of 300, and have 300 over 595, 50.42.
Teachers, please pardon this interruption. Would you please check the missing TALPAS students list that was sent to you via email last night? We are looking for several of those students on the list. Please check your email from Mrs. Vandevort for missing TELPAS students. Thank you.
What is the probability of being a female and eats breakfast regularly? So we are looking for the overlap. This isn't or, which we'll kind of get into a little bit in our next lesson. What is the probability of both occurring at the same time? So I go up to my table, I go to females, I go to eats breakfast regularly. There's 110 counts in that cell. So I'm going to do 110 over 595, 18.49. This is kind of similar to what we did very early on in the school year when we were dealing with categorical data. A female or eats breakfast regularly. So I am going to be dealing with something that is not mutually exclusive. So I'm going to get a count for female, a count for breakfast, and then I'm going to have to subtract that overlap in order to get the true probability for this statement. So females, we said, was 275 over 595. Eats breakfast was 300 over 595. And the probability of both was 110. That gives me approximately 78.15% chance of selecting a female or someone who eats breakfast regularly. And for our last example of the day, the hair and eye color of a group of women were measured. The results are shown below. We have eye color, we have hair color, and we're selecting one random woman, and we're trying to see the probability. So I'm going to do part B first because I think it goes into helping you solve part A. What is the probability she has red hair and green eyes? So I'm going to go to that overlapped cell, which is here, green eyes, red hair, 7 out of my sample space total of 313, which is approximately 2.24%. But now I'm going to use this overlap to help me answer question A. Should have flipped these questions thinking about it, but hindsight. So now I want to find the probability of red hair or green eyes. So I'm going to get my total for red hair, which is 37. I'm going to get my total for green eyes, which is 31. I'm just going through and adding these values together. And that's going to give me 37 over 313 plus 31 over 313 minus the overlap. Because remember, it was counted twice. It was counted once for green eyes, once for red hair. So we need to subtract that overlap. And that's going to give me 61 over 313, which is approximately 19.49. I know